Hey, I'm back again with the Atoms and Elements tutorial. This is Mr. Shrum, and we left off on this table here. We were given elements, their atomic number, the number of protons, the number of neutrons, and the mass number. So we have all the information we need to fill out the rest of the table. So let's start with oxygen. The atomic number equals the number of protons. You see how helium has 2 and 2, sodium has 11 and 11, chlorine has 17 and 17. Well, oxygen has 8 protons, so the atomic number is 8. And we can also do the reverse. Since carbon has an atomic number of 6, we know it has 6 protons. Now we have to look at the mass number to fill out the rest of the table. The mass number is the number of protons plus the number of neutrons. So here we have 2 plus something equals 4. That means there are also 2 neutrons in the nucleus. Same for chlorine. The mass number of protons plus number of neutrons is 35. We know the number of protons is 17, and that means there's 18 neutrons. And then lastly, for sodium, if you add the number of protons plus the number of neutrons, 11 plus 12 equals 23 for the mass number. Ta-da. Cool, so good job. And you'll find similar questions like that in the mastery tests, not too difficult. And now we're going to look at the chemical symbols and how it's represented. The chemical symbol is always written with the first letter capitalized, and it's usually the first 2 letters. Sometimes it uses the Latin root word, so it looks a little different. But this is lithium, for example. Capital Li is the chemical symbol. Then it's sometimes written in full right underneath it, lithium. And then the atomic mass number, sometimes it's rounded like this one is. And then on the left-hand side, we have the atomic number 3, and then the mass number rounded to 7. And then the charge in the upper right-hand corner. That will tell you if it's an ion or neutral. This one has no charge, so it's a neutral element right now. And this activity uses another simulation, and I'll just show you the answers right now. The chemical symbol shows it's a short form or an abbreviation of an element. It's just a quicker way to describe what the element is. What does the number on the top left of the symbol show? Well, that's the mass number. That's the number of protons and neutrons in the nucleus. What does the number on the bottom left symbol show? The bottom left number is the atomic number. That's the number of protons in the nucleus. What does the number on the top right show? That shows you the charge, and if it's 0, that means the charge is neutral. That means the same number of electrons equals the same number of protons. All right, cool. So now we're going to talk about the periodic table. The periodic table shows all of the elements that we know of, right? The table shows natural elements and elements created in a laboratory. We call the rows periods. So horizontal rows are called periods. And it has 7 periods. And we call the vertical columns groups. And there are 18 groups. And there is a bit of weird, sometimes the periodic table doesn't look as organized as you think it is, but it's hard to show it all in its natural state. So we'll get into that a bit later. But an element's position in this table shows its atomic number. So atomic numbers always increase by 1. By counting where an element is in the periodic table, we know its atomic number and its number of protons. The atomic number of nitrogen, N, is 7. Its position in the table is 7th. So we have 1, 2, 3, 4, 5, 6, 7 for nitrogen. Then we have 8, 9, 10, 11, 12, 13, 14, 15, and so on. So it goes through 1, 2 period, and then it goes to the next period, and then the next row, Okay. So that's how it's organized. And another key feature of the periodic table, it shows electron levels. Each row is an energy level. For most elements, the outermost level is only partially filled with electrons. These electrons are called valence electrons. So these are the outermost electrons. They allow atoms to bond and form elemental or compound substances. We can easily find the number of valence electrons for elements in the first 3 rows. Just count how far along in a row the element is, and that number is the number of valence electrons. Many properties depend on valence electrons. The image shows elements with similar properties. The 3 atoms have different numbers of levels, but they all have 4 valence electrons. Does that make sense? So carbon has 2 in the inner level and then 4 on the outer level. Silicon has 2 in the inner, 8 in the outer, not in the outer, but the second level, and then 4 in the outermost level. So you see how carbon only fills up 2 levels, silicon can get up to 3, and then germanium can get up to 4. But they all have the same numbers of electrons in the last energy level. And we can easily find the number of valence electrons for elements in the first 3 rows. Just count how far along in a row the element is, and that number is the number of valence electrons. And many properties depend on valence electrons. These account for the bonds, that may be how attractive elements are to other elements, those types of things. Now open the simulation again and play a game about atomic structure of elements. Click game and then click the picture of the periodic table. Okay, so game, periodic table, there we go. Okay, so 6 protons, that means the position is 6. So we have hydrogen, helium, lithium, beryllium, boron, carbon. Remember, carbon has 6 protons. And since we have 6 electrons, that is a neutral atom. Positive protons equals the number of negative electrons. Yay. Cool. So we have hydrogen, but it's an ion because the number of protons does not equal the number of electrons. Let me turn down the sound a little bit. All right, so we have 2 protons in the nucleus and 1 neutron. And we have 2 electrons. So 2 protons, that will be helium. We have 2 protons and 2 electrons, so that's a neutral atom. Protons 10, neutrons 11, electrons 10. So we know that we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Neon has 10 protons and 10 electrons, positive charge, positively charged protons 10, and then 10 negatively charged electrons, so it's neutral. And then lastly, we have 8. So if we know carbon has 6, nitrogen has 7, oxygen has 8. Number of protons equals the number of electrons. It's neutral. There we go. Excellent. That was fun. But yeah, hopefully you understand that. Now, okay. Wait. Okay. Anyway, so we have another check of information. See if we're learning, right? An element's position in the periodic table provides information about its atomic structure. Use what you know about the atomic structure to complete the table. So hydrogen, the atomic number equals the number of protons. So that's 1. Lithium, we know the symbol is Li, capital Li. There. Atomic number of 3 means the number of protons is equal to 3. Nitrogen, the atomic number equals the number of protons, so that's 7. Number of valence electrons. So now we're going to look at the periodic table. So nitrogen is here, and then we count the vertical groups over to see how many are in the outermost layer. So we have 1, 2, 3, 4, 5. So there's 5 in the outermost level of electrons. So you can do that for the first 3 rows. There, yeah. You can do that all the way up to argon. But when you get to these, the 4th row down, you can't quite do the same, or it's not quite as easy since you have these other elements. But yeah, so we know that nitrogen has 5 valence electrons because we counted over 1, 2, 3, 4, 5. Let me get back. There we go. So 5 valence electrons for nitrogen. We know Al is the symbol for aluminum or aluminium. In other parts of the world, they call that. Sulfur has an atomic number of 16. That means the number of protons is 16. And since 6 is the only one left, we know that the number of valence electrons is 6, but we can also look at that. Here's sulfur in the 3rd row, and we count over vertically 1, 2, 3, 4, 5, 6 sulfur. Cool. And let's double check. Excellent. So cool. So these are good practice examples to see if you know how to use the periodic table, how to read it, and yeah. And now we're going to look at the properties of elements and why it makes sense that they are where they are in the periodic table. This is Dmitry Mendeleev. He is on a stamp printed in Russia, and it commemorated the 175th anniversary of his birthday. So very important scientific figure. And the periodic table is one of the world's most important scientific documents. And he made it all the way back in 1867. Now, it wasn't complete, but he organized his table according to the properties and atomic weights of the 60 known elements at that time. Elements are substances that contain only one kind of atom. Atoms are the chemical building blocks of all matter. As a result, elements cannot be broken down any further by chemical means. What's fascinating is that Mendeleev didn't know about the structure of atoms. Watch the video to learn more about Mendeleev's life and how he created his periodic table based on patterns. So I'll include that. Yeah, we can watch that. Let me share the sound too. There we go. Turn on the captions for those folks that like subtitles. Cool.
Dmitri Mendeleev had a very strange history. You see, he came from Siberia, the backwash of the Tsarist Empire, and he was the last of 17 children. And as a consequence, his family lived in total poverty. In fact, his father went blind and eventually died, leaving his family in tremendous poverty. And then his mother, in one of the great stories of self-sacrifice, his mother basically gave up her life to make sure that her youngest son had an education.
His mother uprooted the entire family and took him to St. Petersburg, where she tried to persuade local universities to take him and train him.
Well, of course, they said no. He's from Siberia, the backwash. And yet, just before she died, she was finally able to get her son into one of the academies that then launched his great scientific career.
As a young man, Mendeleev became famous for his quick mind and quick temper. He was impatient and very argumentative.
He was very driven. He was very determined to do what he set out to do. He was very stubborn.
He also became rather eccentric. He grew a long beard and hardly ever cut his hair, but he was totally dedicated to his work. Mendeleev knew everything there was to be known about the 63 elements then discovered, and he was determined to find out about their relationship with one another. And when Dmitri Mendeleev made up his mind to do something, he didn't give up until he was fit to drop. Though he was a very impatient man, he used to calm himself down by playing patience. The aim of the game is to sort all the cards into the right order and the right suits, which was not so very different from what he was trying to do with the elements. Mendeleev took a sheaf of blank cards and wrote down the names of all the 63 known elements, together with their atomic weights. He began puzzling over his cards, trying to see if he could place them in groups. But try as he might, he could not find a pattern. He was due to leave on a long journey, but he told his driver to wait. He puzzled over his cards a few hours longer. He sent his driver away. Shuffling the cards around the table, he felt sure that he was on the brink of a breakthrough. But after hours of struggle, exhausted, he fell asleep. He began to dream.
The halogens.
And as he dreamt, the picture started to become clear. He awoke with a start and arranged the cards in the pattern of his dream. As a result of his extraordinary dream, Mendeleev cracked the problem. And this is what he came up with. A table with all the 63 elements he knew about, all laid out in one big array. What he'd basically done was to put them in order of increasing atomic weight, going across here and then across here and so on. But he'd also managed to get all the families together. Look here, the alkali metals, lithium, sodium, potassium, rubidium, cesium. These are the ones that react so violently with water. Then the alkaline earths, beryllium, magnesium, calcium, strontium, barium. And over on the other side, the halogens, fluorine, chlorine, bromine, and iodine. He was so sure that he'd got it right that he also made a really important discovery. Just look at these gaps.
Gaps.
Gaps where elements should have been, but none existed. So he made a prediction. He said, and he had the daring to say, that perhaps these are the elements we should look for.
There were several gaps. There was one between aluminium and indium, another between silicon and tin. Scientists aren't usually hailed as geniuses when there are holes or question marks in their work. But in this case, those holes were crucial. Those holes were the things that everyone else had failed to spot, because they signified the positions of elements that hadn't yet been discovered.
Yeah, okay. So the personal life of Dmitri was pretty intense at first, and it goes to show you that being persistent and having some type of humbleness, humility, right? So despite having gaps in his findings, he didn't think to trash the whole thing altogether. He was able to predict that there were elements that were undiscovered and that would fit into his organization, his organized table. So very cool. As we move from left to right in the periodic table, we see three major kinds of elements. You have these metals, which are the purple. You have metalloids, which is this gray area. And then we have non-metals, so hydrogen, helium, and these elements to the right of the table. Most of the elements are metals, and these metals are solid with high melting points. Solid metals are shiny and malleable, which means they can be easily shaped. They can be used as conductors as well, because they're really good at conducting electricity, and heat passes through them easily. Most non-metals are gases, so think hydrogen, helium, neon, argon, those types of things, radon. Solid non-metals are dull and brittle, and that makes them very easy to break. Solid and liquid non-metals are not very good conductors of heat or electricity. They also have low melting points and boiling points. The properties of metalloids are between metals and non-metals. So this gray area, they're kind of like this, well, literally a gray area between those metals and non-metals. Some sets of elements in the periodic table have similar properties. These elements are found in columns 1, 2, and 13 through 18. The set of elements in each column is called a main group. Let's take a closer look at the main groups of 1, 2, 17, and 18. Elements in group 1 except hydrogen, and in groups 2 are very soft, solid metals. These elements are very reactive. That means they easily form compounds with other elements. They're very eager to fill their electron shell. So we have lithium, sodium, potassium, we have beryllium, magnesium, calcium, and in those first two groups. And then the elements in group 17 are also very reactive. So on the other side of the table, they're very reactive. However, these elements are brightly colored nonmetals that vary from gas to solid. So these guys want to react. These guys want to react. However, group 18 has almost completely non-reactive, non-metal elements. All of these are gases. They're very set in their ways. They don't need to react because they have the full shell of electrons. And so we'll talk about that. The names of the main groups and other sets of elements are shown in the image. Group 1 we call alkali metals. They are highly reactive metals. And then we have alkaline earth metals in the second group. Elements in group 17 are halogens. And then we have group 18, noble gases. Mendeleev organized elemental substances into groups based on their similar properties. Recall that many properties depend on the valence electrons. Group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Group 17 elements are 1 electron short of having a filled outermost level. Group 18 elements have outermost levels that are completely filled. So group 1 and 2 have 2 valence electrons. That means they want to get rid of those electrons so they can be stable. Group 17 are almost, they need to gain 1 or 2 electrons, or they need to gain 1 electron to fill that outermost electron level. And then 18, they already have what they need. They don't need to react with anybody. Okay, so we'll pick up where we leave off next time. We'll start with the atomic model, and I will see you all later. Bye-bye.